I welcome you all in this lecture on optimization with modeling of engineering problem, and this is a sub module for the course modeling and simulation of dynamic systems through which you are going through. This is the last lecture among the 40 lectures which we have covered, and in this lecture my aim is to take up some examples on optimization, some engineering examples of optimization, the concept of which we have seen in the previous lecture. Okay. So, this is what I intend to do here. So, we begin with by taking a simple problem, and we will see that from a given statement, problem statement, how can we formulate an optimization problem. Okay. And after that we will be seeing the two ways, that is the graphical method and one of the search method, to see how can we solve an optimization problem. So, coming back to the optimization problem formulation, we can take a simple example. Say that there is a machine weighing say W Newton, and this machine is supported on 4 helical spring, and load on each spring is F, which will be nothing but say W by 4. Now, the question is to formulate the problem to find out say the wire diameter, the coil diameter and number of turns for the minimum weight. So, it is like this basically. Say we have a machine, and this machine is supported on say 4 such springs. So, I am just showing the 2 here, all right, and one of the spring I can show in detail, say something like this. Okay. So, here and certain load F is say applied from here. Now, in this one if we look at say the area of cross section of the wire is this one. So, this has got a diameter D, the diameter of the wire, and the coil diameter we can take say coil diameter is given by this one, and so this is capital D, and N is the number of turns. I have exaggerated it little for you to understand it. We are given the deflection of the spring is limited to 2.5 millimeter, and say the shear stress in spring is limited to 69 megapascal, and the natural frequency of vibration of the spring is to be greater than say 100 hertz. So, these are basically these all statement from here to here are the constraint. Okay. And it is given that use the following relation, say stiffness of the spring given by G D to the power 4 by 8 D cube N, where G is the shear modulus, D is the small d is the diameter of the wire, capital D is the diameter of the coil, and as I said small n is the number of turns in the spring, and the shear stress in spring tau is given by Ks 8 Fd upon pi d cube, where F is the load which is coming on the individual F spring, and of course other terms I have already defined, and Ks is the shear stress concentration factor. The natural frequency of vibration of spring Fn is given by 1 by 2 under root kg upon W, and here if you substitute for k from here, this is the equation which we get. Here also we are substituting for W as well. So, suppose we are given these things. So, now the question is that how we are going to formulate the optimization problem. Now, the optimization problem essentially consists of three things. The first thing is the design vector, okay, and then we have the objective function and we have the constraints. So, these are the three things which we have to write from the problem statement. So, in this case, as I said, our interest is to find out small d, that is the wire diameter, capital D, that is the coil diameter, and the number of turns. So, d, small d, capital D, and n, these are the design vector. Okay. And the objective function fx is, as I said, we want to minimize the weight. So, objective function is given by this equation where say pi d square by 4 is the area of cross section for wire, and of course, this length goes up to pi d. So, for 1 turn this is going to be the for 1 turn this is going to be the total area of total volume, and n is the number of turns. So, we will have the total volume of the spring. Okay. So, this is what is to be the objective function. Now, coming to the constraints as given in the problem, first constraint is the deflection of the spring which is given by F by K. So, this del is equal to F by K, that we can find out from that equation, and this has to be less than equal to 2.5. So, from here I can write it in another form, that is G1x, that is I want to write this less than equal to less than in the form of greater than. Okay. So, I take I reverse it. Okay. So, this is what I get. So, this is one of the constraint based on the deflection of the spring. The other constraint is the shear stress constraint. So, I write expression for shear stress, that is Ks 8 Fd upon pi d cube, and this is should be less than or equal to 69 megapascal. So, I am writing 69 into 10 to the power 6. Okay. And again if I want to write it in the greater than form, then this is how it is to be written. So, I take numerator denominator in the numerator and numerator in the denominator by reversing it. So, this is what I get. So, G2x, this factor has to be greater than 1. Then coming to the natural frequency, it is given that this natural frequency has to be greater than or equal to 100 hertz. So, this is the expression which is given to us, and I make it greater than or equal to 100. Okay. So, the greater than criteria is G3x, this root g small g d divided by 200 and root 2 rho pi d square n. Okay. Now, here you can see that in these constraints and the previous constraint here, we have not considered the equal to sign. So, since it is not included in the constraint, the design variables has to be restricted to the positive values, that is the diameter cannot be negative, small d, capital D, and n cannot be negative. So, these values has to be taken more than 1 more than 0. Now, so this is how we can formulate the problem by writing the design vector, optimization function, and the constraints. Now, let us look at optimum design concept. There is a broad classification of the optimization technique, okay, and this classification comprises of indirect, or what we call it as optimality criteria method, okay, and the direct or the search method. The optimality criteria are the condition a function must satisfy at its minimum point. So, this is based on which we decide upon the optimization, okay, optimum value. And in case of the direct or search method, what is done is that we start with an estimate of the optimum design for the problem, and thereafter we keep on narrowing down our search area, and iteratively we try to reach to a optimum value. Okay, so optimization method, as I said, can be classified based on optimality criteria or the search method, and of course then again these can be applied for the constant problem as well as for the unconstant problem. Similarly, the search method can be applied for the constant problem as well as the unconstant problem. Now, one of the earlier ways of finding out the optimal solution has been the graphical solution. Although with the invent or with the popularization of the computers, this method has become obsolete, but since it is a graphical technique, it aids to our understanding of how we can find out the optimal solution. Okay. So, just for you to understand, I have included this method and I will be explaining this method by taking a simple example. So, the graphical solution, as I said, optimization problem having two design variable can be solved using graphical methods, okay, and all constant functions are plotted and a set of feasible design for the problem is identified using graphical methods, okay, and then the objective function contour are then drawn and the optimal design is determined by the visual inspection. So, this is how the graphical method works. Okay. So, it is applicable for the two design variable. First we plot all the constraint and then we plot the objective function contour and then we determine or identify the optimal design. So, I am going to take a small example, that is say the beam design problem for optimization, and as we have seen in the previous example, first I will give a problem statement and then the data and information collection will be identifying what are the design variable, objective function and what are the constraints, and finally we will be going for the graphical solution. So, let us see a problem statement. The problem is that a beam of rectangular cross section is subjected to say a bending moment and a maximum shear force. Now, the bending stress in the beam is calculated by say 6m upon BD square Pascal, okay, and the average shear stress is calculated as say tau is 3V upon 2 BD Pascal, where B is the width and D is the depth of the beam. Now, the allowable stresses in bending and shear are given say 10 Newton per millimeter square, which is same as that of megapascal, and the 2 Newton per millimeter square respectively. Now, it is also desirable that the depth of the beam should not exceed twice its width and that the cross sectional area of the beam is minimized. So, this is our problem statement. So, from this problem statement you can see that we are talking about the two design variable and these design variables are the B and D, that is width of the beam and the depth of the beam, and the objective function is the cross sectional area of the beam is to be minimized. So, this is the objective function and other things are the constant. For example, the bending and shear stress values are given. So, this is constant. Similarly, the relationship between depth and the width of the beam is given. So, that is also a constant. So, the data and information which are given to us, say the bending moment applied is say 40 kilonewton meter and the shear force say 150 kilonewton. Okay. So, although I am not going to solve this problem completely, but I will be telling you the entire process. Then is the identification definition of the design variable. So, the two design variables are defined as I said, and these design variables are the depth of the beam and the width of the beam. Okay. Both are given in a consistent unit, so millimeter here. Then as I said, the objective function for the problem is the cross sectional area which is expressed at B into D, BD. Then identification of the constant. So, as I said, there are three constants, and these are the bending stress, the shear stress and depth to width ratio which is given. So, we can find out these values. So, bending stress 6m upon BD square. So, m is given to us 40. So, that is converted into consistent unit. So, this is the bending stress. Then we have the shear stress 3V upon 2BD. So, I substitute the value of V here. So, I get an expression for the shear stress, and the allowable bending stress value is known to me, that is 10 megapascal, and allowable shear stress value is also given as 2 megapascal. Okay. So, what are going to be the constants? So, the bending stress constant is going to be that this value, okay, minus 10 should be less than or equal to 0. Okay, or whatever stresses, the bending stresses are being developed, this value should be less than 10. Okay. So, this will be giving us the bending stress constant. Similarly, I can find out the shear stress constant. Okay. So, that is that this value should be less than the given value, that is the allowable shear stress. So, this minus 2 should be less than or equal to 0. Similarly, we can have the third constraint, that is the depth be no more than twice the width. So, depth minus twice of width has to be less than or equal to 0. Okay. And since both design variables should be non-negative, it means that we will have the two more constants, that is G4 and G5. So, minus of B has to be less than equal to 0, or you can say that B has to be more than 0 because it has to be non-negative. This is another way of writing it if we want to write all the constant in the form of less than and equal to sign. So, minus B should be less than and equal to 0. Similarly, minus D should be less than or equal to 0. So, now we are talking about the graphical solution. After defining the design variables, objective function and the constants, now it is to be solved. Okay, the optimal value is to be determined. So, here what is done is that we have the two coordinate axes are drawn along, say, the x we are plotting the width, and along y we are plotting the depth. Okay. So, this is my objective function. My first constant is this one. So, G1 is equal to this minus 10 should be less than or equal to 0. So, for plotting purpose we take this one equal to 0, and by giving the different values of say B, we can find out the value of D, and then we can join all those points and we can plot. So, the G1 can be plotted like this. So, you can see this is your plot for G1. Okay. Similarly, this was our second constant, G2 is equal to this value minus 2 should be less than or equal to 0. Okay. So, again for plotting purpose we take equal to 2, give a value of B and find out the value of D. From this expression we will get a point, and then we plot all those points, join all those points in order to get the contour for G2. So, this is my G2 contour. Okay. So, this is being plotted. and then we have the contour for G3, that is D minus 2B less than equal to 0. So, here again we take equal to sign, and for a given value of B find out the value of D. So, this is going to be a straight line expression passing through the origin. So, this is my constant G3 is equal to 0, fine. And then we have minus B less than or equal to 0 and minus D less than or equal to 0. Now, remember here we are emphasizing that this value should be less than or equal to 0. Okay. So, we are essentially interested in the region nearer to towards the 0 side, okay, towards the 0 side. So, that is why you are seeing this hatching, all right. So, this is how we do plot all the constraint here, okay. So, either we do manually or we can take the help of some of the software, say MATLAB, and the constraints of the problem can be plotted and the feasible region is identified. Now, here note that the cost function is parallel to the constant G2 because the cost function involves BD and the G2 constant also involves BD. So, the cost function is naturally going to be parallel to that of this one, okay. BD is equal to constant. So, therefore, any point along the curve AB represents an optimal solution. So, we are going to have infinite number of optimal design, and of course, this is a desirable situation since a wide choice of optimal solution is available in order to meet the designer's need. So, from here the optimal cross section area can be find out. This is 112 500 millimeter square, and point B here of course we are looking for the optimal, as I said, optimal curve. Our objective function curve is going to be parallel to this G2, okay. So, here the B value we can find out which is from here. Similarly, we can find out the another value A, okay, from here, that is the intersection of these constraints. So, these points basically represents the two extreme optimal solution, and all other solution lies between these 2 points A and B of the curve, okay. So, this is how it is, and this way we can find out the optimal solution. So, the graphical method which you have seen, this is easier but tedious, and it is limited to 2D problems, okay. And the other method, that is the differential calculus method, is not suitable if your derivatives are not continuous, okay. So, in this scenario actually it is the search based method which appears to be promising, and in direct search method actually what we do is that we evaluate a function at sequence of points, say x1, x2, xn, and compare values in order to reach to the optimal solution x star. So, the direct search method is done by either we go for the exhaustive or the total search, okay, which of course is going to be less efficient because we are going to do an exhaustive search, or we go for some efficient search method such as golden section method or Fibonacci method in order to find out the optimal solution. So, we will be looking at the single variable search technique. These single variable search technique which I just talked, they are efficient techniques, okay, and they are applicable for unimodal function, okay. The unimodal function are basically the functions within a certain interval, if that function increases monotonically to a maximum and thereafter decreases monotonically, Okay, that is what I want to say, is that it has got only one hump or one depression within a defined interval. Then we call that function as the unimodal function. Okay. So, this is what it is. Now, one of the very popular method, the search method, which is an efficient search method, okay, because it does not carry out the exhaustive search, is the golden section method. Okay. So, this golden section method is based on the golden section rule, and this rule actually deals with division of an interval into two unequal parts such that the ratio of the smaller to larger interval is equal to ratio of larger to the whole. So, if you look at here, say this is an interval, and we divide this interval into two parts, say R1 and R2, then as per the golden section method, the R2 by R1 will be equal to R1 by R. Okay. That is the smaller segment length divided by the bigger segment length is going to be equal to the bigger segment length divided by the whole length. Okay. So, this is what is on which the golden section method is based. Now, what we do is that in this one we know that this R is equal to R1 plus R2. So, I substitute this R is equal to R1 plus R2 into this expression. So, what I get, R2 by R1 is equal to R1 by R1 plus R2. So, this one is there, R2 by R1 is equal to R1 by R1 plus R2. Now, what I do the cross multiplication. So, I have R1 square here, and here I have R2 R1 plus R2 square. Now, what I do, I divide the whole expression by R1 square. So, here I will be getting 1, and then I take that to the left hand side. So, I have the minus 1, and here I get R2 by R1 whole square, and here I will be getting R2 by R1 square. Oh, sorry, this term is R2 by R1 square, and here I will be having R2 by R1. Okay. Minus 1 is equal to 0. So, this is a quadratic equation, and if I solve for this quadratic equation, I get R2 by R1 is equal to 0.618. So, this R2 by R1 is equal to 0.618 is basically applied for the search. So, in the golden section method, the search is applied. If the search is applied, the interval of uncertainty is reduced by a value of 0.618 times. Okay. So, this is what is meant by it. So, by repeated application of the rule, the interval of uncertainty after say n evaluation is reduced to the initial value of uncertainty I0 by this one. So, In is I0 into 0.618 to the power n minus 1. Now, let us see that how this search is carried out. So, suppose this curve shows the unimodal function. As I said, it has got only one depression. So, this is the example of the unimodal function. Okay. Now, in this unimodal function, say we have the two boundaries, BL is the lower boundary and BU is the upper boundary. Okay. So, the interval of search I which we define is going to be BU minus BL, that is the I will be BU minus BL. Now, the question is, we have to search in this region I, that is BU minus BL, but from where to start the search, that is the question. Okay. So, in golden section method, what is done is that the first point is placed at 0.618 I from BL. So, from this BL I take 0.618 I and I place my first search here. Okay. And but for comparison purpose we need 2 points. Okay. So, where should we take the second point and then we should compare. So, for the second point what we do is that the second point is placed again at 0.618 I from BU. So, from this BU I take 0.618 I and I find out this point. So, this is basically XL and this is basically XU. So, this way I find out these 2 points, I evaluate my function at these 2 points and then compare. So, my XU is 0.618 I and of course, this is from BL. Similarly, my XL is this one 0.618 times I and this is from BU. Okay. So, evaluate the function at these 2 points and then make a comparison to see if function value at XL is more than function value at XU, and of course, this is the condition for minimization. Okay. So, we evaluate function value at XL and we evaluate function value at XU. Now, what happens if fxl is greater than fxu? So, if this value is more than this one and if we are looking for the minimization, okay, and we have already assumed that the function is the unimodal function, then what we do is that we remove this part of the segment for our search. Okay. Because we have already seen that fxl here is more than fxu. So, we are not interested in finding at the left hand side area of the XL. So, in this case we confine our search to region right of XL, otherwise confine our region to the left of XU. Okay. So, we confine our search in this area, and if this is not the case, then we confine our search in this area. And then after this we find out a new interval of uncertainty is defined using the same approach as the first case, and the process of evaluation is repeated until an interval of uncertainty is obtained that is equal to the desired tolerance which we are looking for. Okay. So, with this I will complete this lecture. You can look for these 2 books, very good books by Professor Arora and Professor Rao on optimization. Of course, these are books in itself, say a full 1 semester course which I have tried to cover in 2 lectures, but this will give you an idea. Okay. So, thank you, and thank you for enrolling in this course and participating in this course. Wish you all the best.